Continue hearing more about precision measurements, and Bethlem will tell us about molecular fountains.
Thank you. I'm not sure if it's on or... Is it on? Yeah, good. So, thank you very much for having me here. I'm not sure if I should be glad that you put me after the big guns, but anyway. So, I will talk about two experiments. One being our molecular fountain of ammonia molecules, and the second one being a new project which we're working on, or which is new for us, doing an EDM measurement on barium fluoride. And this is just starting, so I'll just tell you how far we are. And I don't have time to talk about methanol, but this is just here to remind our previous speaker how molecules rotate and that you have masses and stuff. Good. So the molecular fountain. So this is a machine that we built in our lab, which is 2 meters tall, and this is our molecular fountain. So we start from the bottom with a pulse valve of ammonia molecules. And we use decelerators to slow down the molecules to, in principle, a standstill. So we started out with this stock decelerator, which actually 20 years ago Gerard Meijer explained here for the first time. And so now we have tried with this stock decelerator, but it's turned out to be very difficult. And we switched to a second decelerator, which works better or is more gentle with the molecules. And this helped us to really, to make this fountain, as I will explain you now. So this is a picture of the, going very fast. This is a picture of a ring decelerator, and in this decelerator we make a moving potential. So we have a series of rings, and we apply voltages in such a way that we make a minimum of the electric field which travels along the molecular beam line. And so what we do is we decelerate with the first decelerator, we decelerate molecules to about 90 meters per second, and then we trap them in one of those minimums, and then, we first take them along, then slow down the minimums, bring them to a standstill, and then actually, we play tricks with them. So as I will explain. So anyway, so this is an image that this is pictures of the molecules at the end of the decelerator. And I showed different time of flights here, which all correspond to different settings of the decelerator. And this one just shows you that we guide molecules at 90 meters per second. But then, of course, to make it more fun, we start decelerating to 80 meters per second and then actually accelerate back to 90 and detect it. And we can do this to actually decelerate all the way to 0, have them there for a while, and then accelerate back to 90 meters per second and again detect the molecules. And the important thing of this is that actually the signal roughly stays constant. And this has been a large struggle and to get it this far. And but now actually the number of molecules really stays constant throughout the deceleration process. And so once we've decelerated them, bring them to a standstill, we of course can trap them in this case for 20 milliseconds, and we can keep them for 50 milliseconds and just as long as we like, and still have the same number of molecules, which is density or number. So we have a very difficult thing in that, as I will explain later, we detect molecules in a laser focus. So we detect only a very small subset of them. And from that, we can calculate back how much molecules we have, but it's very unreliable. But this should be about 100,000 or so. Good. But, so in the end, we actually we care mostly about how much molecule we can detect in the end, of course. But I will explain. Good. So once we have them trapped, we can play tricks with them, and one of the tricks that we would like to play is, of course, trap them and then lower the potential. And in this way, we do adiabatic cooling. So this curve shows you a measurement where we trap them, and then we trap them initially at 5 kilovolts, Then we lower the trap depth to 2 or 1 or even lower kilovolts, and then we either lose them or we cool them, and it depends on how quickly we do this. So if we do this very rapidly, then we just lose molecules, and that's it, and that's the red curve. If we do it very gently, then actually the molecules follow, and you see that we have much more molecules at lower temperatures. And if you zoom in here, then you can see that if we lower the depth of the trap to about 1 millikelvin, then we still have more than 10% of our molecules left. So we have really a sample of molecules below 1 millikelvin and play with that. Okay, so that's the biggest ingredient of our fountain. So once we have those molecules, we then very gently push them upwards into a quarter pole. And this quarter pole again focuses the molecules, and it does it actually in such a way. So we apply voltages, pulse voltages to the 4 quarter poles rods. So there's one missing here that you can look on the inside. But you see the trajectories of the molecules here, and we apply voltages such that we make a focus here where we detect them, and a second focus here where they go through a bunch of rings which we use to cool the molecules in the z direction. And then finally they're up here, and then we switch all the voltages off, and the molecules are in free flight as they fly up, and we wait until they fall back, and then we focus them back and detect them. And sorry, my throat hurts, but good. So that's what we're doing, and the trick of this is that we up here we have a very big cloud, which is very cold. Actually, the temperature is below 1 microkelvin, but they're in a big space, like 1 cubic centimeter. Up here, where we detect them, we focus them very tightly, and there we detect them with our focused UV laser. And here we have a high density, and so we can detect the molecules. Anyway, so this is then an image of what we see when the molecules fly upwards. So again, this is different time sequences applied to the decelerator and to all the high voltage electronics. And we set this in such a way that we send up molecules with a velocity of 1.9 meters per second, which is this one, all the way up to 1.4 meters per second. And of course, the slower they go, the longer it takes before they reach the detection region. So that's why you see, well, this takes longer. Anyway, the interesting thing happens when we, of course, look 200 milliseconds later. And then we see the molecules falling back. And now, of course, the opposite happens. So if we send them up with 1.4 meters per second, then they take 50 milliseconds before they return to the detection point, and we detect them. If we send them up with 1.9 meters per second, they actually spend 266 milliseconds upwards and before they arrive here at the detection region. So the time that I put here is actually the time that the molecules are in complete free flight. So during that time, all the electric fields are off, and in principle, we can use it for doing precision measurements. And this is, of course, what I would like to show you in the next slides, but we're not quite that far. So this time is what we've been struggling with, and this is the time, the coherence time that we gain from having cold molecules. So, okay, so I hope you like this graph, because this took me 10 years of my life. Yes, so the reason that we did finally manage to do this is because of 3 things. So the first thing is that we have this traveling wave decelerator, which really now decelerates virtually without losses. And that means that we have a phase space density in the beam now. Well, we don't know exactly, but it must be bigger than 10 minus 11, otherwise we would not be able to detect molecules. Of course, this is a pitiful number for atomic physics, but well, for us this is a big achievement. Okay, so the second thing is that we have now a very compact lens system. So before we had a much better system, but it was much more difficult to actually get it to work, and we never quite managed. The last thing, which is that we use eliminate background by detecting only the slow molecules. And we do this by detecting only, by doing a trick called VMI, and this is a thing which I think Bas is going to tell much more about. But it's a way of imaging the molecules that we ionize onto the detector, and we do this in such a way that molecules with a low velocity arrive exactly at the center of the detector, whereas molecules with a higher velocity will get somewhere else. And so this is what we normally see in our screen, and these molecules here, they're all background, and we don't care about them. This is just the fact that ammonia is very sticky, and it's impossible to not have ammonia in the machine and to detect it. So we always have that, but the interesting part is here within this square here, where we have the slow molecules. And you can see that it helps the background enormously. So this is, this is all ions, just counting all the ions over the whole screen. And if we only detect ions in this square, then you see that we have much less background and still the same signal. And so this is so we are a little bit in between chemistry and physics, and we hope to use all the tricks from chemistry. This is a really chemical physics style measurement, and we hope to use all the advantages of both fields to make this work. Okay, so what our future plans are, of course, what we want to do with this is now do spectroscopy, and ammonia, in principle, can you have many transitions in ammonia which are suitable for doing these precision measurements. So particularly, of course, the inversion frequency, which is a very strong transition and very nice characterized transition. Interesting is also if we could measure transitions around 1.5 micron. So in our lab, we have a 1 hertz stabilized laser, and we could use at 1.5 micron. And if we could use that for doing this spectroscopy, of course, this would be very convenient. So we've been trying to do this, and we've done. I'm just showing you this to show that we have been doing stuff and trying to get this to work. But you see that the line width is still about 1 kilohertz, so we have a lot of problems getting it right. And what we really have two problems. So one of the problem is that we have a lot of hyperfine components because ammonia has 3 hydrogens, and that gives you a huge mess. The other problem is, of course, that we do have very little signal. So we have typically 1 ion per second, which is fine, or it's not perfect, but it's good enough if you have proper signal. But then because of all the hyperfine structure, it's actually too small to get to where we need to go in the end. So we're trying different things to, either to get more signal, and one of the things is actually trying to shoot the detection laser from the top. So in our measurements, our molecular beam looks like a cigar, but like a cigar in this shape. But then our detection laser is, of course, opposite. So the overlap of the detection laser and the molecular beam, or the package which we focus back, is very small. So, of course, what we like to do is send the UV, the laser beam, from the top into the machine. But we, of course, have an obvious problem here, that we have high voltage electrodes, and they don't go very well with focused laser beams. So we try to what we've been trying to do is actually, it would work as long as the laser is perfectly aligned and doesn't move. So this is my student, and he's been working on a system to monitor the laser position and to make sure that it's really perfectly correct. So here on the top, this is where the laser optics sits, and I've promised him that if it actually works, he gets signal, then he gets a proper box rather than this cardboard box. Good, so that's one way we're going, and this now works in the sense that we have some signal, but we haven't really done the real measurement to prove that this gives us more signal. So we haven't looked at signal from the fountain yet. Good, so that's one solution. The other solution would be to shift to another molecule, and of course changing to another molecule sounds attractive, but there are certainly molecules that have a simpler hyperfine structure, But then again, we need all the advantages of ammonia as well. So well, one option would be to go like molecules that are very popular in New England, and see if that would work. And the advantage of that would be, well, that we can do laser cooling, of course, and then perhaps that would be a way out. We'll see. What we certainly want to do is at some point do barium fluoride, and this brings me to kind of the other experiment I want to talk. So we were always been interested in decelerating heavy molecules, but in the old decelerator, the problem was that, well, in the old decelerator we used fields up to 150 kilovolts per centimeter. And this is, of course, fine for ammonia. So this shows the Stark shift of ammonia as a function of the electric field. And, of course, we always look at molecules in this state, which is a low field seeking state. And this goes all fine for ammonia because it's very light. Now, for strontium fluoride or barium fluoride, this shows the Stark shift of strontium fluoride. This is completely different. So if you go up to fields of 100 kilovolts per centimeter, of course, everything becomes high field seeking, and that makes it very difficult. Now, in the ring decelerator, actually, we use very small electric fields up to about 30 kilovolts per centimeters. And then there are states which are still low field seeking, and so we can decelerate heavy molecules in a low field seeking state. And, well, this is what brought us to try to see if we can compete with other people who are measuring EDMs. So we have a new project where we want to do an EDM experiment on decelerated and laser-cooled barium fluoride molecules. And this is paid by the Dutch National Institute for Particle Physics. So we just started, but I'm just going to tell you a little bit of, well, what our plans are and how far we are. So this is what this is what we plan on building. So we, of course, want to use a ring decelerator to decelerate the molecules, but now because barium fluoride is so heavy, we actually need a 5 meters long ring decelerator. So this is our ring decelerator. We want to start with, a Buffergas beam, a cooled beam of about 200 meters per second, and then it should be slow enough to actually that we can decelerate it all the way to a standstill. So that means what we plan on doing initially. So the final goal would be to have a fountain, but initially what we want to do is decelerate them to 30 meters per second, and that gives us an interaction time of 15 milliseconds if we have a meter of if our measurement region is a meter long. In between, of course, the advantage of barium fluoride is that you can do laser cooling on it, and so we want to do transverse laser cooling of the beam, hence make it very bright and make sure that it really doesn't diverge over this 1 meter of free flight, and that we can detect them at the end. So the advantages of this are of twofold. So one is this interaction time of 15 milliseconds is longer than the experiment so far. The other advantage that because we use this transition for laser cooling, we can detect them very sensitively. So in principle, we can cycle many photons, so we should be able to detect all the barium fluoride molecules that are sent through the machine. Good. So let me show you. So this is the machine we've been building, and this is standing in Groningen. And it's actually so long that it is straight, but because it's so long, it's impossible to get on the photograph. And so this is the view from the side. So inside we have 9 sections of that I just showed. So I have one section of 50 centimeters of ring decelerator. Inside here we have 9 others, and they can be used to decelerate even very heavy molecules. So this is an old measurement from 2016, and then we had less sections, but we can guide here. This is a beam of strontium fluoride, and this is the part of the beam that we just guide through the machine. And because they stay together, they end up in a very narrow peak at the end of the 5 meter long machine. So we can decelerate them and decelerate them to lower velocities. And unfortunately, in this case, you do see losses. And that's because we're really pushing it, how much we can decelerate it. So we put in another section and hoping to decelerate them really completely to a standstill. But unfortunately, we probably had problems before and now it became more apparent. So what you see is this measurement that I show here are two measurements done at different voltages. And you see that actually the green one is measured at 3.25 kilovolts. And the blue one is when we increase the voltage to 4.5 kilovolts. And rather than going up by a factor of 10 or 20, which it's supposed to do, it actually becomes less, the signal becomes less when we increase the voltage. So this can mean a whole lot of things, but not very good things. So what's very likely is that either the decelerator is misaligned or we have big losses because of adiabatic problems. And so we actually think that's. So am I doing well in time?
Yes.
Good. So we think that actually the decelerator is not properly aligned. So we actually took them all apart. And so this is a picture I took on Friday. And we have the 9 sections here. They have a card here, which is good, which means that they are now completely aligned. And so we will put them back in the machine in the next month or so. Yeah, so let me talk about the other parts of the setup. So we're working on the cryogenic buffergas beam. Actually, we're working on 2 of them. So one of them in Groningen, which will just be used straight away, and one of them in Amsterdam, which we'll test more and try to optimize more. So I will not try to explain this here, I guess. So this, the first one is now working. So this shows the buffergas beam signal, this one in absorption just in front of the cell, and this one 30 centimeters further downstream. And this is, we have to characterize it more. It's just working now for a couple of weeks. We have to characterize it more, and then once, hopefully, by the time that the decelerator is put together, we can also use this cryobeam as an input and measure with that. So we're also, just building the lasers for barium fluoride and testing things. And so we have a couple of lasers, and we have we have a supersonic beam of barium fluoride, and that works well. So just as a test, we've been using this to actually measure the lifetime of the excited state that we want to use for laser cooling. So we just have our molecular beam, and then we use an AOM to switch off the light very quickly. So we have a pulse train of pulses of 10 nanoseconds spaced 2 microseconds apart. And then we just look at the barium fluoride signal to see what the lifetime of the barium fluoride is. And this is the 2 states. So this is the pi 1/2 and this is pi 3/2, and they have kind of the lifetime that was expected, but we just measured it much more accurately now. Good. So this is a very strong transition, which is good for laser cooling. The problem, of course, is whether the Frank-Condon factors are also good enough. So we've been, so part of the collaboration is our theoretical chemists, and they have done a complete calculation of calcium fluoride, strontium fluoride, and barium fluoride, just to calculate all the states and all the Frank-Condon factors and compare them. Of course, these are very well known, but we're mostly interested in the barium fluoride. So different from calcium fluoride and strontium fluoride, in barium fluoride you have this state, AL data state, which is now not above the state that we want to use for laser cooling, but slightly below it. So this is a leak, and we were very worried about it, and this is the main reason for doing the calculation. But it turns out to be okay in the sense that we do have a leak, but it's still enough to scatter about 2,000 photons, and that should be enough for what we want to do. So that means that it's probably not possible to ever do laser cooling from a buffer gas beam directly. But of course, this is not what we want to do. We want to first start decelerate and then do laser cooling. And that should, well, with this leakage that we have, that should be possible. Okay, that kind of brings me to the end. So this is the EDM team. So the PhD students working on the project and some master students and the old guys here in the back. And these are the people who have done the experiment on the fountain. And with that, thank you.
Okay, we have time for some questions.
We can just make a comment on your laser cooling scheme at the very end. You have this extra delta state that's metastable below the cooling state.
Yes.
It's actually the same case for YO, that we have that state down there. It's a nuisance. It does still decay down, and it will go to the different parity states in the ground.
Yes.
And you can solve that problem by just applying microwave to remixing.
Yes, but we would like not to do that. So I'm not sure if it's for barium fluoride, it's going to be harder anyway, because I think we need different frequencies than for YO. I'm not sure if it's possible. Yeah, okay. Hopefully we don't have to use that at all, and then it'll be fine. Thank you.
So you have the nice data where you would show that you get similar number of molecules whether you decelerate or not.
Yes.
So this shows that deceleration doesn't cause additional losses.
Yes.
Do you have evidence of whether maybe there's just very strong losses or not for just getting it through the decelerator?
You say it doesn't matter whether you're guiding or you...
Because if there's non-adiabatic heating and whatever, it's going to be maybe independent of whether you're actually trying to slow things down in the process or not.
That's very unlikely, though, because the time scales that you decelerate and you are very different. So if there's any loss, then that has to be more so when you start decelerating or do different things. It's very unlikely that it stays constant all the time.
The number of stages you go through would be the same.
Yeah, but it's true. Well, to answer your question, no, we don't have it, and I'm not sure if I would
Maybe
expect
there's
it.
some evidence that you have, I think it's experiments where you go across, then you go all the way back, and then you go forward again.
We could do that. Yeah, we don't. I mean, we've tried things like that, and we didn't characterize this in all detail, but I never saw anything worrisome. I mean, we do. If you want to be very picky, you would say that actually at 5 meters per second here we have loss. And this is actually true. I mean, we repeated this many times, and we do have a dip here at 5 meters per second, and this is when you go through a resonance. So if we go very slowly through a resonance at 5 meters per second, we will have losses. But normally, if we go directly to zero, we go so quickly through it that we don't see it, and then we don't have a problem. So there are losses in the decelerator if you do it wrong, but if you do it right, we never see anything. Yeah.
What do you mean by resonance theory?
This is a motional resonance. So once, this is particle physics in a way as well. So it oscillates in forward direction and sideward direction. When they start to couple, we can have losses from the trajectories become unstable. So that's what's happening at these points.
Maybe one quick question. So, for ammonia, what specific precision measurement experiment you're looking at? So that's it. That it's sensitive to.
Yeah, so ammonia is interesting. Well, the inversion frequency of ammonia is very sensitive for the proton mass. So certainly that transition would be very interesting. In a way, I don't care much about what molecule to use at the moment. I mean, if we could do a measurement at 1.5 micron and have a transition and align with a 1 hertz line width, then we could always use this for looking things at constant variation of constant and things like that. Yeah. For now, I would just like to have the record of the most precise transition, but well, I should not say that now, but when I've done that.
Do you have a plan to put the methanol into the fountain?
I have a dream, but no plans. No, methanol is too difficult. So ammonia is already very difficult, but methanol is so much more difficult to make a proper beam out of it that is probably not possible.
But remember, there's this extended degeneracies, which gives you a linear structure there, which is suitable for your decelerator.
Yeah, you mean like molecules like with OH groups attached to it? Yes, that would be very interesting. But methanol itself is very difficult to make a beam out. And actually, a Buffergas beam might work, but then I'm not sure what the density is. The problem is so ammonia is already so difficult that anything that becomes more difficult seems too difficult.
Okay, thanks, Rick, for this interesting.